For the electrophile in the SN2 reactions, we're going to first look at what is that environment like around that alpha carbon, what else is attached to it, and how does that affect the reaction itself, so that SN2 reaction. So in this example, we have two different electrophiles. We have A and B. If we're thinking about that alpha carbon, we can label it, that's the one that's attached to the leaving group, so that's our alpha carbon. In each case, we see that the alpha carbon for the first one is attached to one other carbon and the leaving group. The other two that we're not showing are H's. For the alpha carbon in the second one, we have two carbon groups attached and then the H that we're not showing and the leaving group. So this is going to be our major difference here, what that environment around that alpha carbon looks like. What does that translate to for our transition states? So when we were looking at nucleophiles, we were kind of using a consistent electrophile. We were always kind of using the same one while we were comparing our nucleophiles. Here, we're going to use the same nucleophile as we're comparing electrophiles. So we're going to use our OCH3 minus as a nucleophile. So for transition state for A, we're going to have our OCH3 minus, our nucleophile coming in, and we're going to have our alpha carbon. So if we want to number these carbons, we can number them 1, 2, and 3, and then here we'll do 1, 2, and 3. Let's label them in our transition state. So carbon 1 is, and for A, is going to be our alpha carbon, so that's our carbon that we've drawn out. Then 2 and 3 are the other two that are also attached to it. For the transition state B, we have our alpha carbon actually being carbon 2, that's what we're attacking, and then 1 and 3 are the other two. It doesn't really matter which one we chose, is 1 or 3. But those are going to be the other two carbons. So that's why we drew our transition states the way that we drew them. What's different here, we've always kind of been seeing examples where these are both H's. This one is actually a CH3 because of the fact that that alpha carbon is also attached to another CH3 in addition to this one. And so that's why we've drawn it a little bit differently here. That really gets down to why one transition state would be lower in energy than the other. So for the transition state for A, we're going to have a steric interaction between our nucleophile and the other carbon group. So this is a smaller nucleophile. It's not going to be super large steric interaction, kind of like what we saw in the previous a few videos ago with the larger nucleophiles. This is still going to be a steric interaction as this nucleophile comes in with its own group. So the oxygen is going to attack, but it has still its own group attached to it on the other side of the oxygen that we have to worry about. That's going to have a steric interaction with the group that's on electrophile A. For transition state B, we actually have the steric interaction present on both sides. So as this nucleophile comes in, it's going to see both groups, CH3 1 and 3, and we're going to have two steric interactions here. So we're going to have a steric interaction with both of those groups, and the H's that are attached to that carbon right next to the oxygen, we're going to start to see that steric interaction there and there. We're going to have a more steric interaction in transition state B. What we saw about having more steric interaction in a transition state, that's going to raise that energy of the transition state. That's not good for these reactions. We want that transition state energy to be lower. And so our better electrophile in this case is going to be that one with the lower energy transition state, which is A. So that is more stable transition state, which is another way of saying lower in energy. Reason for this is that we have less steric interactions than in the transition state we're comparing it to. So transition state B we're comparing it to. So we have less steric interactions than in transition state B. That's going to mean if the transition state itself is lower in energy, we're going to have a lower activation energy for the reaction, assuming that same nucleophile. That's going to mean we're going to have a faster reaction. So that's going to mean that electrophile is going to be a better electrophile. So same thing with nucleophiles and electrophiles. If it's able to do the SN2 reaction faster, it's better. And so with our less sterically hindered electrophile, we're able to do that reaction faster. So it's going to be a better electrophile. Let's take a look at what that looks like on this reaction coordinate diagram. So in blue, we have our better electrophile. That's that blue path, lower activation energy because we have a lower energy transition state. And that's because we only have that one steric interaction with that one group on our alpha carbon. The other one has two steric interactions, so more steric interactions. It raises that energy, and it's going to have a higher activation energy, slower reaction for that one, which is this transition state. The blue one is going to be the lower energy path because we only have that one steric interaction. And what we can do with this example is we can actually look at other types of electrophiles and try to extrapolate what we had just learned here. So steric interactions being very important. So for our electrophile structure, this really influences that rate of the reaction. So the ones we were dealing with a primary and a secondary alkyl halide. And so, primary and secondary alpha carbon by extension. So our primary is when we have one group attached. Our secondary is two groups attached. So in our example, these were both CH3 groups, these two R groups. In our example, it was a CH2, CH3 group for this R in our primary example. And so we said that the primary is better than the secondary. That makes sense here. We could take it down one to be even more favorable. What if we had no carbon groups attached to that alpha carbon? Well, that's going to not have any steric interaction. So comparing it with the same nucleophile, we're going to end up having a very fast reaction, very little amount of steric interaction in the transition state, very low energy transition state for what we call a methyl electrophile, where we just have H's attached to the alpha carbon in our leaving group, a lot of room to go in that alpha carbon and attack it. So these are actually really good electrophiles for our SN2 reactions, and that's going to be very fast. Primary is going to be after that, so we will have that one steric interaction, that one group kind of causing problems, but not too bad. With our secondary electrophiles, that's going to start to get more crowded, and this is about as much as that SN2 reaction can take. We can only go up to secondary because as soon as you introduce a third group around that alpha carbon, a third carbon group, that is too high energy. So that transition state is completely out of reach for our SN2 reaction. So we're actually not going to see an SN2 reaction at all with tertiary electrophiles. And these are ones that the alpha carbon is going to have three carbon groups attached. So being able to identify that electrophile as methyl, primary, secondary, or tertiary is going to be really important for deciding, can you even do an SN2 reaction? Or if you can, which one's going to be faster? Which one's going to be that better electrophile in the SN2 reaction? And so that really comes down to that structure around that alpha carbon, whether it's methyl, primary, secondary. We can do the SN2 at least. When you start to become tertiary alpha carbons, they can't do SN2 because that transition state energy is way too high, too many steric interactions. We're not able to do the reaction with our tertiary.